Welcome back. In topic 1, we try to get a big picture of advanced convection in terms of its scope and nature. In topic 2, we'll focus upon governing equations. Topic 2, Part 1, Interpret mass and momentum equations. A. Focus. In order to avoid being buried in tedious mathematical derivation, to lose the sight and focus, we will use two-dimensional governing equations rather than three-dimensional, without losing any essential features of a governing equation. We select two-dimensional in x and y direction. As a result, the velocity and all the derivatives in z direction are 0. The flow is still incompressible, therefore density is constant. In Cartesian coordinate, now we have a new set of governing equations: mass, momentum, energy, and viscous stress tensor. B. Mass conservation. First, we have our finite two-dimensional in x and y direction flow over a plate and a differential control volume dx dy taken from this finite two-dimensional flow. Second, for such a control volume, the mass conservation states that the rate of change or mass within control volume equals the rate of mass flows into the control volume minus the rate or mass flows out of a control volume, where m dot is the mass flow rate, density, velocity, area. Since the flow is incompressible, the density is constant. Therefore, there is no mass change within the control volume. As a result, the mass conservation has a new mathematical expression in equation 1.4. Now, you're ready to interpret the mass conservation equation 1.5, which is also called continuity equation. First, the first term is multiplied by the differential control volume dV because all differential equations are per unit volume. Then we take a constant density into the derivative and represent the differential control volume dV with dx dy dz. Next, we take dy dz into the derivative. Now, density times x direction velocity times the surface area is the flow rate in the x direction. Finally, we apply the Taylor's expansion to get mass flow rate difference. Therefore, the physical meaning for this term is mass flow rate into the control volume minus mass flow rate of control volume in x direction. Second, for the second term, we follow the same steps to get the mass flow rate difference in y direction. Third, if we bring the first term and the second term back into equation 1.5 to get equation 1.8, the physical meaning for the mass conservation is clear, which is all the inflow minus all the outflow per unit volume is 0, indicating there's no mass change within the control volume. C. Momentum conservation. First, we have a differential control volume and it moves with the flow. Therefore, the Newton's second law can be applied to this fluid body. Second, if the total force acting on the fluid body is summation F and it moves with acceleration A, the Newton's second law states that sum of forces is equal to mass times acceleration. In scalar format, like in extraction, sum of extraction forces is equal to mass times extraction acceleration. Now, you're ready to interpret momentum conservation equation, which is the restatement of Newton's second law. Summation of forces is equal to mass times acceleration. First, let's examine the left side of the equation 2.3 after it is multiplied by the differential control volume dV. 1. Density time control volume dV gives mass. 2. The first term is derivative of extraction velocity over time. It is acceleration and it is local acceleration because at the same fixed point, like a point 2, the velocity only change over time. 3. The rest of terms is representing velocity carrying velocity gradient and moving around. This acceleration is called convective acceleration because at the same moment the velocity only change over the distance. For example, we all know when the water flow going through a nozzle, the velocity is increased and the flow is accelerated, even though the velocity may not change over time. So, in quick summary, the left side equation is mass times local acceleration plus convective acceleration. Second, let's examine the right side of the momentum equation 2.6 after it is multiplied by differential control volume dV. This represents the sum of forces. 1. Force, we all know, is a push or pull acting on an object, such as fluid body. you may run into many different forces, but all can be grouped into two categories. One is a body force that can act over distance, like gravity. The other is surface force that must act through direct contact, like the pressure force. 2. Body force, gravity acting on the differential control volume. Gravity between a mass and the Earth is its weight. Therefore, in general form, the body force is equal to mass times gravitational acceleration. It is a vector. It has 3 components in the x, y, and z direction. For the last term in the equation, rho times dv gives m times gx. It represents the x direction component of body force. 3. Pressure force on the surface of the differential control volume. We know that pressure force is a normal force acting on the surface, and it always toward the surface direction. Therefore, in general form, the pressure force equals pressure times the surface area. For the first term in this equation, we represent differential control volume dV with dx, dy, and dz. Next, we take dy, dz into the derivative. P, pressure time area, is the pressure force. Finally, we apply the Taylor's expansion to get pressure forces difference. Therefore, this term represents the pressure force acting on the left face and the right face of the control volume. In quick summary, this represents the body force, this represents the pressure force, and this represents the viscous force. 4. Viscous force is a surface force associated with fluid viscosity mu, velocity gradient, and area of contact. For example, if you put 2 plates in between is let's say honey, and if you try to push the upper plate, you can feel the resistance. That resistance is our viscous force. 1. The Newton's law of viscosity states that the viscous shear stress tau, which is it's a viscous force per unit area, is proportional to the velocity gradient. The ratio between the viscous stress and the velocity gradient is viscosity mu. If the mu is constant, the fluid is called Newtonian fluid. 2. In general form, the viscous stress has this unit, is a second order tensor. It has 9 components for 3D flow, and it has 4 components for 2-dimensional flow, with 2 normal viscous stress, 2 shear viscous stress, 2 in the x direction, 2 in the y direction. For example, the normal viscous force in the x direction is normal viscous stress times the area perpendicular to the surface. The shear viscous force in x direction is the shear viscous stress times the area which is parallel to the surface, parallel to the viscous. And this is our so-called friction force. After this brief introduction about viscous force, you're ready to interpret the middle term, which is viscous force. We use example 2 to demonstrate. First, this is a stress tensor tau equation, and this is a mass conservation equation, and this is our differential control volume with normal viscous force and shear viscous force on it. First, we take constant viscosity into the derivative, and then break second order into 2 first order, and represent differential control volume dV with dx dy dz. By checking this term related to normal viscous stress tau xx, this is related to the shear viscous stress. Next, we will add 0 term to this equation because the mass conservation, so is 0 and its derivative is 0 as well. After some mathematical manipulation, we will get exactly the normal viscous stress and shear viscous stress. Next, we will bring in the surface area dA into this derivative, and surface area dAy into this derivative. And as you can see, tau xx times dy dz is the normal viscous force, tau yx time dx dz is the shear viscous force. Finally, we apply Taylor expansion to these two terms to get the normal viscous force difference and shear viscous force difference. Therefore, the physical meaning for this term is sum of viscous forces in x direction, this all in x direction, acting on the faces of differential control volume. In a quick summary, the right side of momentum conservation, this is gravity, this is viscous force, and this is pressure force. At this point, we covered topic 2, part 1. If we do a quick summary for Newton equation or mass conservation, it represents all the inflows minus all the outflows equals 0. For momentum conservation, the sum of gravity force, viscous force, and pressure force is equal to the mass per unit volume time local acceleration plus convective acceleration. See you next time. Have fun.